Thank you very much. Thank you for the introduction. I'm really honored to be here. This is the first time that I come to this country, and this is really lovely. I really enjoying my time here. Well, I talk today about large data, big data associated with exascale computing. And maybe if I have to summarize some of the takeaway is not just that it's difficult and what are the technical challenges that are involved in that, but also that the techniques developed on the research front are actually very useful in practice and can have a very strong positive impact in society. My background in computer science, I'm established a center at the University of Utah. There, the focus in dealing with large data, so we have a core of professors in data mining, visualization, high-performance computing, databases, and so on. And those are all related areas that actually are important in developing advanced application in this field. Generally, we try to tackle application across several domains, and here is just a little overview of some of the things, and I'll go through examples later. Application that goes from turbulent combustion, subsurface modeling, dealing with large-scale imagery from satellites and or microscopy, and definitely heavily rely on HPC infrastructure. But that's not the only direction. Definitely we look at unifying the application developed from a computer science perspective and make sure that they have a broad application across various disciplines. Generally, we look at specific applications so that they motivate the work and help deploying things in practice. This is for example, an application for space awareness. The little dots you see around the Earth are actually real satellites that go around the Earth. And here we're looking at the yellow part is actually debris of a satellite that was shot down by the Chinese government, and the US wanted to track down possible damage. And again, there was a cycle of simulation of different scenarios, seeing what happens, impact on different environments, and so on. And the infrastructure to make that work was kind of the interesting part of the challenge. Here, very different application, but much more on fundamental science. This is a turbulent mixing between two different liquids. This turbulence is kind of what happens at the interface when gravity push one down. And this is interesting because actually this is what happens in the explosion of a supernova or in a nuclear bomb. And so this is kind of a type of fundamental physics that people study very heavily. But to study those things, you have to go through a simulation that generates quickly tens of terabytes that you have to go over and over through and study and analyze. And again, the challenge is really big in terms of moving the data, analyzing the data, and so on. Generally, the areas that we try to apply in different combinations range from, of course, dealing with the performance of processing, moving the data. So definitely HPC and exascale have a big role in here. There is a lot of emphasis on data analytics with a variety of application area, from statistics, topology, geometry, and so on. And some of the example I'll show later focus specifically on using topology. But then there is a lot of user interaction, usability. The tools, especially in visualization, have to be simple to use, otherwise they don't make an impact. And so for this reason, then we focus on very specific application area and trying to build the whole spectrum from data source to fruition and understanding. Technically speaking, for high performance processing of the data, we look at, for example, way of organizing the data. Use the example you see on the top right is used, for example, space filling curves to organize the data in a way that make it very fast to access without using very expensive hardware. And then in combination of how you process the data while it moves, with the data streaming techniques, multi-resolution, computing things out of core, so using kind of your disk as if it was main memory, and still not being paying a big performance hit. For the analysis itself, we use a lot of topological techniques, where we take data from a really large spectrum of applications and then extract features like maxima, minima, saddle points, ridge lines, and basically in all those examples we have those vector representation with lines and surfaces that replace the original vector data and still allow to do the full analysis with like orders of magnitude data reduction that really improves the way things are represented. So I'll go through a few examples just to give a sense of the advantage of using those techniques and how they impact. So here, for example, we deal with this porous medium where it collects this micrometeoroid. Is actually something that goes into some of the spacecrafts and collects space depth, and they want to understand from those cavities the speed of the impact, the size of the particles, and so on. And this is simulated on a large supercomputer, and then we actually build this topological representation. You see the raw data gets replaced by this simple multi-resolution graph model that allows to understand in detail the structure of this porous medium. And now we go from terabytes to simply gigabytes of data, and the representation is actually even more effective to measure the depth of the cavity, the stress, and the failure of the material in a way that is represented in the simulation. In fact, we can take this graph model and use it as an input in other application cases. Here is a case of analyzing the performance of the material that is in the batteries that you may have in your phone. This is simulations run both at Lawrence Livermore National Lab and Argonne National Lab. And here you see that from the raw data, we build this graph model. That graph model is not informed yet that we're actually dealing with the molecular dynamics simulation, and still actually represent very closely, without bias, those cycles where the charges of your battery get properly trapped or leaked. And so here we can measure those cycles. If they are six-sided, like an hexagon, then the battery in your phone will last very long. As soon as you start having defects and those cycles have 7, 8, 9 sides, you get low performance, leaking of charge, and so on. And then they're using the simulation to design better and better batteries. So here, instead, we're looking at a simulation of combustion where they're trying to design new fuels. This is a mixed fuel based on hydrogen. And those are the topological structural regions that they call extinction and reignition. Those are characteristic of this type of burning. And if they understand the dynamics of those regions properly, they will actually be able to reduce the temperature and increase the efficiency of those fuels so that you reduce pollution and improve the performance of the fuel. Those are techniques that we're using for moving and processing large data. They find quickly and easily applications outside of the more traditional scientific domain. Here is a case actually where a group at Stanford collected very high resolution data of the David of Michelangelo. This actually was for preservation of the artifact. This is more for cultural reasons. But still the data was so big that they couldn't distribute it. They couldn't deal with that. So they came to us and we built this app you can see Gigapixel David, you can actually download it on your phone, where they can directly download the data set and visualize in full 3D this super high resolution data set. And what's interesting is that the challenges in terms of storing, streaming, and processing the data are the same that you deal with, even if at different scale, that you deal with when you're using a high-performance computing infrastructure. So the work here, though, applies heavily in the study and understanding of scientific data of various types. And here we have been looking at how to allow scientists in the climate modeling space to deal with the massive data collection that they're dealing with. So with this ability to reorganize and stream and process the data, we allow them, for example, on the fly, integrating in their own infrastructure the visualization of evolution of cloud formation, temperature, and so on, doing statistical processing on the data. So here you can see that not only they do the traditional visualization, but they have a scripting layer where they can decide how to average multiple simulation runs, highlight various regions of interest, and very quickly come to scientific insight, even if the data sizes are truly overwhelming. And I'll show another perspective on this use case a little bit later on. So in general, we try to target practical live demonstration of how the infrastructure works, so that people can get familiar and use it in practice. For example, at Supercomputing Conference, we have been deploying a visualization environment that is connected to a supercomputer. This was the SC14. This is the visualization environment connected to Shaheen, so down in Saudi Arabia. Here is where we're connecting from it was in Denver, connected to Chicago, where we're looking at simulation executed on the Mira machine. So that's 750,000 cores. What's interesting is that we're really serious about scaling, and not just in the thousands or 100,000 of core, but all the way down to the small devices. So the I/O library that we are deploying now goes all the way down to smartphones, iPads, and so on, to desktops, Powerwall display, all the way to the largest supercomputer in the world. And I think that's a really important way of dealing with the software and make sure that it's useful in practice for a variety of applications without having to redo the work many times. So this is, for example, a use case where we have been dealing with large data set generated with this advanced photon source at Argonne National Lab near Chicago, where the science application people were actually located in Washington State. And there they were running those experiments. Here you see on the left the image of the data being generated. And this was really literally saving people millions of dollars, because traditionally they would just go there, rent a facility, go back and look at the data, and if they did any mistake, they would have to go maybe 6 months later and redo everything from scratch. Here they could stream and visualize it on the fly, look at the results, and adjust the experiments while they were ongoing without the risk of waste of any resources. Here, it's kind of one of the extreme cases that we deployed very recently. It's really ongoing work at this point. NASA has this very large data collection it's really a single data set of 3.5 petabytes. So we're not talking about just terabytes anymore. And it's an open data set, except nobody can look at that because it's so big that they tell you, well, give me a piece of storage, I'll get you the data. And just nobody has that. And so what we did is, with our infrastructure, we established a portal at Lawrence Livermore National Lab with a small cache of 100 terabytes. And now we have a simple web viewer. I have a URL there, and people are curious, I can show a little demo later on, where actually people can connect, and just on a regular browser, on a regular laptop, they can actually go and traverse and explore this multi-petabyte data collection, something that before was totally unthinkable. In fact, other than our approach, they're still using kind of large offline processing that takes a very long time. The impact, though, does not go only on the super high scale. Here is data set from Microscope labs. This data set alone is 6 terabytes. Obviously, after the petabyte seems relatively small, but it's still actually really challenging. And here I show, for example, how people can actually visualize, process, and explore in real time a multi-terabyte data set on a small laptop without needing of a special machine. Again, this is something that target very well what's called the long tail of science application, not just the high end, but the large number of science labs that they cannot afford very expensive resources. They can still use these classes of tools. In terms of scaling, we're not only talking about the computing side, even in terms of displays. We can target the high resolution displays on very cheap commodity hardware. This is the display that we have in Utah, and with 36 monitors, 9 PCs, and just with $50,000 you can have a massive kind of data center type of capability. And we went to other locations where they have much higher quality. What's interesting is that to deploy something like this, it took us maybe 1 or 2 hours. So it's also very simple to use and very effective. And again, it sadly makes the infrastructure easy to access for the public. Going back to the specific of scaling to large HPC resources, here I'd like to just give a few numbers just to give us the sense of the capabilities. In general, our component allowed to connect directly to a simulation, dump the data in a format that can be streamed on the fly. And kind of this is the plot that probably I'm the most proud of. The black line shows the scalability of our I/O library. It's called PIDX. And the other two plots show the two top competitors out there. And here you can see that ours is the only one that was able to get to the full Mira machine, 750 million core. This was done achieving 80% efficiency. So effectively, there is very little margin to improvement. The machine was actually used as best as it could. How we're doing this and how we're extending, we're actually building a data processing pipeline and data reorganization that is based on a graph model. Is actually what's similar, related to what Thomas was talking about yesterday, except we build a layer on top of that and we target different runtime systems so that we make it also easy to program for people that want to use it. So this is kind of the layers of the stack that we're working on. So with the top orange layer is our data flow infrastructure that is actually fairly easy to use. And underneath, we connect to existing runtime system. In particular, in the recent work, we have been targeting Legion, MPI, Chum++, and we have been showing that our top layer make it very easy to use without losing much of efficiency. So comparing native implementation with respect to specific execution in one of the models, the performance penalty was minor, but the effectiveness in terms of people time to build the solution is much, much better. So we have been targeting a few classes of application. They're very different from each other, so they're good representative of possible solution. In situ topological analysis have shown kind of how useful it is. Here we're looking at how well does it scale. Visualization like volume rendering, isosurface, that's fairly obvious. And also we have an application in brain study, so in neuroscience, and as part of the brain initiative, we're looking at how to deal with large-scale brain data with this type of infrastructure. So this is the case of the topological analysis for combustion data. The multi-scale model is actually based on the data reduction graph that we see on the left. And the features are what you see in the picture on the bottom right, those little extinction and reignition region for this particular combustion. What's important is on the top right, there is the scaling plot for run on full Titan machine, and where we show the difference between data analytics processing compared to traditional HPC, where actually using fewer cores, collecting data is practically more efficient, so we're going towards a concurrent execution of multiple analytics at the same time, instead of parallelizing a single one at the same scale as the simulation. Here we have a case of the brain data, the basic task of taking a large data collection and then looking at overlap between different regions and registering and aligning that. When you start looking at tens and hundreds of those, it takes a really long time. And so here we're using this parallel infrastructure to actually ingest the data into the supercomputer, do the parallel processing, and then send it back to the scientists for exploration. Already, this is work only done in the last 6 months, but we already got totally unprecedented scaling numbers. People in this field have very little familiarity with parallel computing infrastructure, and here we manage very quickly to enable use of thousands of cores, and of course we already know that our infrastructure can aim at really much larger. More importantly, the scaling is nearly linear, so we know that as the brain initiative make progress, we will be able to deal with larger and larger data sets. This is the type of infrastructure we are aiming for. There's going to be some devices like a microscope. Here we have a 2-photon microscope. Those are really, really high resolution microscopes. There are newer ones that are going to be even higher throughput. And so we enable visualizing the results on the fly while connected to a parallel computing infrastructure, and then build these global solutions that you see kind of in the top right. Now, as I was saying at the beginning, I like to highlight the fact that a lot of those things may sound like esoteric, high-end solutions that are really good only for research or really high-end science. The reality is that we are actually working on the fact that we scale from the small to the big. We're really looking at solutions that have an impact on the industry front. So in collaboration with the university, we have a spin-off that actually is looking at opportunities for commercializations. And in that case, you really want to look at what people do in practice. You don't need to use the largest supercomputer in the world, but the class of technology is actually very important. So for example, they started to using some of our data streaming infrastructure to deal with large-scale oil and gas data sets. Those are very high-resolution outcrop data, and actually people are using directly this for training geologists and deal on a low-end device like an iPhone and iPad to get access to data sets that normally would require a large desktop or a large server, and still being able to use it very effectively. In healthcare, the possibilities are really large. The scanning devices are coming into the application of histopathology, for example, similar to what we see in microscopy. And so here they're looking at deploying infrastructure like the one that we have been described for using telemedicine, especially actually targeting small hospital in rural areas, exactly because they don't have the money to buy large resources or manage them. And so since our technology actually makes really efficient use of very cheap hardware, this actually becomes a very good match. I was showing before this massive visualization of data, petabytes of data from climate data. The reality is that we got a request from hospitals in Argentina to visualize high-resolution mammography data so that we were able to store in Utah. And because of the streaming infrastructure that was easily accessible, we have even a version that runs on a web browser. And now suddenly they can build a repository and have doctors do a diagnosis remotely, even if doctors don't like to live, especially good doctors, they like to live in an expensive city. So how do you give access to regular people to a high quality doctor that is not going to move in a small area? So actually here we had experience with this ARAP Labs, also a spin-off of the University of Utah. They have been using those tools in practice, and here I'll show just one small clip of an experience that some of the people in that space. You have the voice or not? Oops.
And so I started using this program, and what I found is it allows us to do a lot more. We can ask students to do homework assignments, identify things, ask questions. Eventually we'd like to use it to give exams. It's almost the same as using a microscope. It allows you to move around in pan. So
the important takeaway is really that, so the tools have very high-end potential, but can be used like in a classroom. There we did a test with like 140 students. They were doing the diagnosis, they were turning in homeworks via email. All got really easy compared to very expensive infrastructure they're trying to use before and use it in practice. Here, it's a deployment that we're doing for people in neuroscience. They have those microscope, and they're really desperate for software that ingests the data. In fact, they were using the $1 million microscope at lower resolution than the maximum, simply because the software couldn't handle the size of the data. So we got in collaboration with them, and so we allowed them to visualize the data at full resolution, and even allow them to look at the data while it was streaming out of the microscope. Again, similar to the high-end case that we were looking at in the Argonne. Here, they were looking at this data sets that would take them weeks to ingest, and they would find mistake much later and waste a lot of time and resources out of a very sure expensive piece of hardware. Here they could do all in real time, catch mistakes, and do the best use of something that they actually can afford very little and they have to share among other researchers. And one last application area that is actually also benefit from this type of technology, something that started for us more as a research project in digital photography for collecting large panorama and stitching them into single pictures and then analyzing, like you see like this. Now actually there is an effort to actually commercialize it for agricultural sector. So to get high quality information regarding the fields, they fly drones that collect the data, and so now you get this very high resolution data, much higher quality than satellite data, because it can be taken from drones that fly at low altitude, but requires on-the-fly stitching of massive amount of images, and then distribution in, again, rural areas where the capability in terms of internet, cell phone connectivity, and so on are very low, and so the resources are extremely limited. The upside, though, is that now the farmers, the consultants, they can make a very informed decision about how much water to use, how much pesticides and hydrogen and so on, and actually there is a real potential to save a lot of money and increase productivity in a field that really today it's important. So to conclude, the areas that we have been working on to develop scalable technology that on the high-end targets exascale computing involves performance tools, data analytics tools, a high focus on usability and user interaction, and in many ways target specific applications. And I must say, actually, I'm particularly excited to the way this meeting was organized, exactly because this merge of research, industry, and so on. And I'm really a strong believer that the confluence between university research, and national labs, and industry are key to motivate new research and build solutions that can have a real impact in the world. And I'll thank you very much for your attention.
Okay, thank you for your interesting talk. May I ask for some questions or comments? Okay, yeah, please.
So you are dealing with medical data, and you know in North America it's very sensitive. If you collect
Yes.
data in Argentina, it's okay, maybe it's okay, but in Otta, then
HIPAA is the...
how you handle the security and privacy?
Yeah, so so our infrastructure is actually built as a library that we can plug in an existing environment. So we're dealing with, yeah, for people that didn't hear, the question is how we deal with the security layer on top of medical data. That's true actually for many other applications as well, but there are lots of regulation, especially in the US, I guess in Canada as well, regarding medical data. The way we deal with that is actually we try to plug into existing security layers and then let those create channels of secure communication that gives a hit because the encryption has some cost, but fortunately the scaling of the infrastructure still allow to achieve high performance even if we're going through limited bandwidth channels. But it's a very good practical question, and that's the reason why we're looking at a few small hospitals in Utah as a pilot program, but we are seeing much more kind of aggressive tendency for adoption outside of the US. And I have the impression that the US will pay actually for all those regulations because new technology will pop out outside before it gets adopted inside.
Okay. Yeah.
Can you hear me?
Concerning the fact that
Oh, there are two questions, I guess.
Okay, first.
Hopefully we can take them both so there is no...
Concerning the fact that post-processing and post-processing visualization might be expensive, is really expensive.
Yes.
And there are some practices like, for precision reduction to make it faster, cheaper. And then the problem of reproducibility pops out and it becomes a concern. Is it also a concern of your work or not?
So, yeah, let me just summarize. You hit two key problems. The word post-processing, which depending on which side you like could be pre-processing, and reproducibility. So first of all, so I didn't have time to get into the detail, but we're trying to virtually remove the notion of pre-post processing. So the notion of offline, going through the data maybe to reorganize it or to take it down to a smaller size. So for example, our I/O library dumps the data actually faster than traditional I/O libraries, but is already reorganized in a multi-resolution fashion so that when you do a query for analysis and visualization, you don't have to do any post-processing. It's done. So there is a huge set of opportunities in kind of wasted data processing and movement in traditional technology, and we're really trying to overlap data reorganization with data movement so that post-processing will kind of go away as a concept. The other side is that some techniques like topology or mining and so on, they do massive data reduction. Now, you're right, reproducing the results becomes a real problem if you throw away the raw data, in the sense that if I build an abstraction and then that's the only thing I keep, it's potentially a problem. The way we try to deal with that is actually, for example, in topology we have a very strict error bounds. So if we are forced to throw away the raw data to keep only the topology summary, we can at least say precisely within what error the results is provided. So it can be at least guaranteed at that level. Still, when you want to drill down and get the pieces of the data that was original, I mean, yes, if you throw it away, that's gone. Another aspect is that, though we also allow very selective saving of the data, so even those are images, we actually turn that data more like an AMR. So during the processing, we can flag which areas are likely to be important and which area are likely to be boring in a way. And so throw away only the stuff that it's unlikely to be needed and still keep high resolution version of small pieces that you might want to. But again, those, again, you never know if later on you want to look again. So I think there was another question.
Yeah.
I hope that answered.
Yeah.
First, good morning to you and the audience. My question is, if you could answer actually.
Sure.
What was the network infrastructure that you use for transferring all those big, huge amounts of data that is in agricultural points? I'm sorry.
Go ahead.
In IoT, what we usually do is like, what the trend is, or what we try to do is to process as much as we can in CPEs, you know, the customer premise. But then you will like transferring all those very high resolution images to the computers. How did you do this?
First of all, kind of philosophically, we do not want to rely on any special high-performance network. Although if it's available, we'll use it, no, don't get me wrong. But I normally give demos of, say, the high-resolution Michelangelo data. I can do it on a phone using not even the Wi-Fi, the cell phone connection. The other is that, and it's kind of related to the answer I was giving before, as we generate the data, and that's true also for the agricultural data, we transform on the fly the data into a multi-resolution model so that people, when they explore the data, they can access very quickly an overview, and then when they zoom down to a location, they can just get the high-quality version of that part. And so we want to overlap the data usage with the data movement so that you don't just move everything and then explore it. You do a lot of things on demand. So for agriculture in particular, given the constraints that are on the field, say people fly a drone, get all the images, they might get on a laptop there or on the desktop on a machine, but again, it's somewhere in the fields. So first of all, the whole system runs even on a small laptop, so it can do everything locally, and then they just use normal cell phone connections. We do not expect, and looking at trends, although people are deploying new hardware infrastructure, the trend in terms of growing the resolution of the data is much higher than the trend of network improvement, that you might as well assume that the networks are now changing. And by the way, Going back to the similarity to Exascale, if you look at the latest Exascale machines, you will notice that the computing power keeps going up. The actual bandwidth of the I/O infrastructure, the network to save the data, is literally flat. Has been flat for at least a couple of years. So there, and that's what we're translating from the research to this practical use. We really have an environment, say, with cameras are getting high resolution, desktops are getting faster, network connections are really not getting any faster. You just deploy, if you get a 1 gigabit connection, you're super lucky. There is no way you will ever get anything like that. You have to be able to deal with very low bandwidth connections, and that's the only way to go, at least in our experience. Hope that answered the...
Okay, another question.
Thank you for your interesting presentation. I have 2 questions. The first question is that which framework do you often use for your visualization and high performance image processing in Utah? For example, OpenCV, OpenGL, or have you developed your own framework in Utah, and if yes, is it open source? And the second question is that do you directly involve with the hardware infrastructure like FPGA, DSP, etc., or you just rely on the cloud computing application with high-level programming and software and applications?
Okay. So first to the first question, what do we use? So for a lot of things we had to re-implement ourselves, not because we like it, so we definitely use anything that is out there if possible, but a lot of the things that we have require a very deep reorganization of the way the software stack is built. The data movement has to be totally integrated, in fact overlap with the data processing and the visualization and so on, and that's something that with the traditional, say, ParaView or Visit, it would not work. We use basically directly OpenGL. That's just because it's a low-level, simple thing. We could use DirectX practically. We have not been using things like OpenCV. We normally use it as a initial test to check what works in terms of, say, what segmentation works. But then normally when we have to make it fast, we need to take a little piece of that algorithm and change it very substantially. Still, the way we are building our platform, actually, we want to make it as open as possible, so that, for example, our library goes into a Python layer, and there, for features that we don't have, you can always bring a piece of the data into OpenCV or some other library. Python is convenient just because it has tons of libraries out there. To the open source specifically, some of the parts of the software are open source, some are not. And I guess that's one of the challenges with dealing with the fact that the university is also commercializing. I would like to say with the people here, we share the code with our collaborators all the time. So it's not close in a true say, in a cultural sense, but we have some limitations. So for example, the PIDX library that does the scaling up to 750,000 cores, we have a hybrid license, so it's open source, it's out there. I can give people the GitHub to download it, and you can just use it. If you go in a commercial application, then there are limitations to that. There are other pieces that we share binaries, but again, that's something that we're trying to figure out in the process. The second question was, sorry, I need a reminder.
Yeah. Do you usually rely on the cloud computing application, or you sometimes involve in the FPGA and DSP and hardware programming, like very
Okay, yeah. So that's a more difficult question. We have done a lot of work kind of on our own implementation, so with custom solution that those. But we have now. We are really would like to take advantage of cloud resources as much as possible. So in one of the programs for the neuroscience, the microscopy application, actually, we have now a prototype where, as the data gets ingested in our server, we use the cloud as an overflow. So we have a drive, say, with 50 terabytes, but if your data collection is larger, instead of buying larger and larger drives, we will actually directly connect to the cloud, and then some of the data processing components will be executed on that. Our main limitation is really that sometime when you use existing infrastructure, the penalty in terms of performance is huge. And that's really a question of design. So some of the existing infrastructure, unfortunately, they are stuck. I mean, the question before about pre-processing, post-processing, some of those infrastructures strictly require that. And sometimes we're allowed to connect to them, but we have to tell people, look, it's not going to be that fast anymore, not even close. So that's going to be a kind of an issue of choice. But in terms of connecting and sharing that, we definitely want trying to make it as friendly as possible.
Thank you very much.
Cool.
Okay, I have one question already answered, but maybe more general. How much your algorithm is independent from software, from hardware platform, I mean, in terms of time complexity, especially in case of data streams, because you need more speed and more precision.
Yeah, I mean, this is the big question, and this is actually what we have been working on for a long time. So we use a lot what's called cache oblivious techniques, and there are more general data organization oblivious and hardware oblivious techniques. So we look at algorithms that scale kind of irrespectively of the characteristic of the hardware, and that's so for example, if I have data that runs in memory, typically when you run out of memory you have thrashing behavior and things don't work anymore. The algorithm we use includes the fact that the data movement can start to be slow, and so even if the data becomes paging in and out, the algorithm is somewhat slower but still actually scale very well. If the network say gets slower, there is no, so typically we don't have a threshold below which things just don't work anymore. They much more gradually slow down, and so this is achieved with this cache oblivious techniques, hardware oblivious, in general with algorithm that theoretical. That's actually interestingly, it's very practical, but it's much more of theoretical work. You can prove that no matter what is the size of the blocks in your data movements, the algorithm will have a certain performance. And we know that practically certain trends still will move data into blocks. The question is going to be what is the size of the block, whether it's through network or between memory and disk and things like that, or caches and so on. Okay.
Thanks again from Professor Pascucci, and I want to ask for next talk. The next talk